right, so to review from what we did before we had our break, extended period of break, let's look at when we just have a single amino acid and we want to determine its PI, draw its titration curve, and look at it at different pHs, or when we lose the different hydrogens that are ionizable. So for example, if we look at aspartic acid, also known as aspartate, if we start off by drawing this guy when it is fully protonated, so therefore all three of the ionizable protons are still present, we would draw it like this, starting off with our N-terminus, or our amino N, with having 3 hydrogens and a positive sign. Our R group on aspartate has an extra hydrogen here that is also ionizable. And then our C-terminus, the carboxylic acid side, has its hydrogen, also ionizable. So if we draw all of them there, and then we can put the pKa1, we would have it look like this until we reach pKa1, which is 2.1. If we are looking at our chart that we had from class, we can see that once we reach this, that corresponds to the carboxylic acid end. On the carboxylic acid end, we will lose our hydrogen, the other two would remain with their hydrogens, and our net charge would be 0. This is also what we would call our Zwitter ion. And then as we continue to change our pH and we reach to the pH of 3.9 corresponding to the pKa of the R group, which is our side chain, we would then lose that hydrogen. And this would cause our whole amino acid to have a net charge of -1. We would continue to do this, or keep this structure, until we reach a pH of 9.8 corresponding to the pKa2, or the amine side, and we would lose that hydrogen and also the charge that you were seeing previously. That would give us a net charge for this amino acid of -2. Then if we were to go on and draw the titration curve for this, and keep in mind that we would have our pH versus our amount of our base or hydroxide ion added, we would have a curve that has 3 buffering regions. These 3 buffering regions correspond to the 3 ionizable protons that we showed above were being removed. And then when we would need to figure out where on this titration curve does the PI land, we would use our PI equation and we would figure out what that value would be. In order to do that, if we had drawn, like we did above, the entire set situation here, we can see that we are looking for our PI, which corresponds to the pH at which our amino acid has a net charge of 0, so that would be this structure right here. In order for us to figure out which 2 pKa's to use in calculating this, we would first find where we have a net charge of 0, and then look at the 2 pKa values on either side of this structure, and we would add those up, divide by 2, and that would give us our PI. We would then be able to draw it on our titration curve to know that that landed between pKa1 and pKaR, and that's where our PI was.